Going less into the theory this time because a lot of this stuff is things that you're going to spend, if you take a linear algebra class, you'll spend significant portions of the class discussing the theory and how to find these things mathematically. So this is not even up there. So this is going to be more a little bit of showing you what MATLAB has for you in these areas, and then some cool things you can do with them that MATLAB makes easier. So to start, this is just, like I said, going to be a very quick overview. Last time we talked about determinants and how they're a specific value associated with square matrices. There are other numeric values that are associated with square matrices called eigenvalues. You're going to hear about them a lot at the end of linear algebra, and then all over differential equations if you have to take that. So without getting too deep into what they are, basically they take, we talked last week about linear independence versus linear dependence and how two vectors are linearly independent if you can't manipulate one into becoming the other, or if you have three vectors, any one of them is linearly independent if the other two can't be combined to form it. So what an eigenvalue does is it changes vectors to make them linearly dependent. And again, it's something that's going to come up a lot in differential equations, but just for now, using MATLAB, you have, let's see, create a 3x3 matrix here. Okay. Forget my brackets. So let's make sure that this is a linearly independent matrix. Determinant isn't 0, so it is. So if I wanted to find the eigenvalues associated with this, I would just type EIG, parentheses A, and that will give me my three, each row has an associated eigenvalue. There's also another associated thing called an eigenvector. Each eigenvalue has an associated eigenvector. If you want those, you can do a double output of PD equal to eiga. And what this will do is each column of P is an eigenvector, and then the eigenvalues are along the diagonal of D. And this is, again, something else that's going to come up in end of linear algebra and differential equations. If you can diagonalize your matrix, it makes a lot of calculations quite a bit easier. So this is a very easy way to find a diagonalized matrix. So that's really about it for eigenvalues, eigenvectors, diagonalization. I just wanted to show you that's how you do it. If you get to the point where you need it, MATLAB makes the calculation a lot easier. So.
Did you already enlarge the screen?
It
looks small.
I don't know what I did. So let's get that. I did not. Thank you for reminding me. Mm-hmm. Okay, is that a little better? Okay. So. The next bit we're going to talk about is orthogonality. To say that two vectors are orthogonal just means that they make a right angle between them. And the easiest way to check for this is, last week we talked about the dot product. If you take the dot product, say you have vector A, vector B, if A dot B equals 0, then A and B are orthogonal. So this can be, this particular thing is going to come up more in the workshop we're doing next week, and also a little bit later when we talk about basis, but it can be very useful pretty much for anything you use vectors for, just to check and see if these vectors are influencing each other at all or not. So if you have, say, two force vectors, if this angle is not 90 degrees, then there's going to be some overlap of these forces. If it is 90 degrees, then they're both pulling along completely different axes, and that can simplify certain calculations. But sometimes you're not going to have that option, so something you can do with this when you don't have orthogonal is you can use these vector calculations to find what's called the projection. So if I wanted to find the projection of F1 along F2, it's basically dropping down and figuring out what is that component of the F1 vector. So right now it looks kind of like F2 is along, if I had a XY axis, it looks like F2 is along the X axis, but that's not always going to be the case. And so to calculate this, you use an equation for the projection of one vector. This says the projection of F2 in direction of F1 is going to be equal to F2 dot F1 over F2 dot F2 times F2. And you're going to go into the whys and what exactly this means in, I think, Calc 3. But one example of how this kind of thing, so if you were to run through this, let me see, let me get a good example up here. So say I had two vectors. And I wanted, and so let's say each of these is some force in a given direction. Now, neither of these obviously is along a single axis. They're pointing off into some portion of three-dimensional space. But if I wanted to find if I wanted to find the total force in the direction of V2, I would want to find how much force V1 has in the direction of V2. So I would use this equation. I would use dot V1 with V2 divided by dot V2 times, and remember, dot products return a scalar value, a single number value. So that's why you can multiply this whole expression by a vector and still have it work. So if I were to do this, I would get this vector here that, so you see V1 doesn't really have a whole lot of force in the direction of V2, but there's a little bit. So if I wanted to find my total force, it would equal V2 plus that answer. So that would be my total force in that direction. So that's a fairly simplified problem, but say one example of how you might use it in an engineering situation is that there's several materials that have specific planes that they are weak along because of the structure of the material. So if you have some, let's just say we've got an airplane wing that's made of a specific material that has a weak plane along the 45 degree, and you've got, say, half a dozen different forces acting on this at any given time, you could, if you wanted to find out what the specific force along that plane of, along that weak plane is, you could turn that into a vector. If you called this your XY axis, you could turn that into the vector 1, 1, and then use this process on all of these different forces, add it all up to find your total force along this particular shear plane. And if it's too much for your material, then you need to go back and work with your design and make it so that the forces better balance each other out, or just pick a material that is stronger or doesn't shear along that particular plane. So that's one example of how this kind of thing would be used. So before we go on, just a quick little challenge and refresher for you. How about you guys take, say, 5 minutes and write a function to do the projection equation. So just to remind you from what we discussed last week, for the MATLAB command, the dot product is dot AB, and yeah, let's start with that.
What's the syntax for defining a function call in MATLAB?
Okay, so yeah, also for that reminder, you start with opening a script. You can either do that by clicking new script or by typing edit into the command window, and then you just type function and then do your definition in the script.
Okay.
So yeah, give it 5 minutes and then I'll run through it, or if everyone's done early, say so.